Hello and welcome back to Calculus 1 Saturday edition. We are going to talk about L'Hopital's rule 4.7. Um, Not exactly his rule, which is interesting. The story of this I found it years ago, and I found it very interesting. Um, this is actually Bernoulli's rule, and L'Hopital was this very rich guy who liked to learn mathematics, so he was paying Bernoulli as a tutor, and Bernoulli used to send him papers and so on. So L'Hopital learned a lot of calculus, and L'Hopital wrote the first ever calculus textbook. So this result showed up for the first time in that calculus book, and initially everyone thought that it was his rule, that he figured it out and so on, and then later on it worked out that it's actually Bernoulli, the one who um, discovered the rule and all of that, but didn't publish it anywhere. So technically L'Hopital's calculus book, the first calculus book ever written, was the place where this rule was published for the first time. Everyone thought it was L'Hopital, so it just stuck. Even though today we know it was not his rule, I guess still to honor his commitment of writing the first ever calculus book, the name remained L'Hopital's rule. Now, what is L'Hopital's rule? L'Hopital's rule is a way to compute limits using derivatives. So we're going back technically to chapter 2, but now we are going to deal with this in a completely new light. So let's write the theorem right away. So suppose f of x and g of x are differentiable, meaning you can take the derivative, and that g of prime of x is not 0. So those are the two things that you need to know. Then the limit of f of x divided by g of x as x goes to some value a is the same as the limit of f prime of x divided by g prime of x as x goes to a, provided, so I'm going to box this, let's go here, provided that f of x and g of x both go to 0 or infinity together. Let's go, both go to 0 or infinity together. So what this means is that we need something that it's called indeterminate form. And that is 0 over 0 or infinity over infinity. So in order for your definition up there to work, I mean theorem, to work, you have to have this particular feature satisfied. Otherwise, it doesn't really work. Now, the best example to start off with is going to be the example for the sine x over x, which I said a couple of times we will eventually learn how to do this. Now you just memorize and so on. So today is the day when we take a look at the limit x goes to 0 for sine x over x. So you were supposed to just memorize that this is 1 and you move along, right? So that's something that you used to just know because we told you memorize it. Now we can finally figure out how to solve it. So when you plug in 0 in x, you get sine of 0, which is 0. And when you plug in 0 here, you get 0. So you have 0 over 0. So we have 0 over 0. And because you have 0 over 0, we can use L'Hopital's rule. And now we put this L apostrophe H on the equal sign to signify that these two have the same result. They are not equal. They're not equal. But they have the same outcome. They have the same answer. And that's what the L'Hopital rule is about. You change your problem so that the answer is easier to obtain, and it guarantees that the answer will be the same. So that's what we have for this particular theorem. So now when I take the derivatives, I get cosine x over 1. Now, these are independent derivatives. This is not a quotient rule. These are just independent derivatives that has nothing to do with the quotient. And now we can try and plug in again, and now we get 1 over 1, which is 1. And this is how we obtain the value of 1 going through this. Now, let's take a look at another problem. Let's say you have limit x goes to 0 of square root of 9 plus 3x minus 3 divided by x. All right, so you try immediately. Remember, from chapter 2 we learned that if you are able to plug the value in and compute the number without any issues, 0 in denominator or whatever else, you are done, right? That's it. Your problem is solved and you are completely done. But if you are not able to do that, you get zeros and a whole bunch of other stuff, then you have to use algebra, or you get to use this rule if you get 0 over 0 or infinity over infinity. So now when I plug in 0, that kills this 3x, and then I just have a square root of 9, which is 3. So 3 minus 3 gives me 0 here. And then when I plug in 0 on the bottom, yeah, that's what it is. So we should be able to take those independent derivatives and see what we get. Now remember, every time you do that, you have to put L apostrophe H on the parenthesis. Otherwise, it's not going to be correct mathematical notation. You cannot say that left side is equal to right without L apostrophe H. Anyway, so what am I going to do? Well, take the derivative. Now, derivative of x on the bottom is 1, so I don't have to worry about that one. Derivative of minus 3 is 0, so forget about that one as well. So all I need to do is to take the derivative of this square root, and that is also very cheap, right? We have 9 plus 3 root x, and the derivative of the inside is this. So now I can try and plug in 0, and what you get is a half. So the limit is 1/2. And you would go, wow, isn't that cool that, you know, we get 0 divided by 0 and now it's a half, and earlier 0 divided by 0 was 1, and so on. Obviously depends on the function. Now, if you have, in some cases, you might end up with problems that look like this. Limit x goes to 0 plus And now you'll see y0 plus. It's because it's ln x divided by the cosecant x. So, right? When you draw the ln graph, you see that as you are going towards 0, your limit is pushing down to negative infinity. Okay, so that's negative infinity on top. Now, what's happening with the cosecant? Well, cosecant is 1 over sine, which means that I'm supposed to draw a sine over here, then put the vertical asymptotes at every 0. And when I have the vertical asymptote at every 0, all I need to do is to invert these cups like this. There we go. Then delete the sine. And this is my cosecant graph. Now, being that this is where 0 is, if you go to 0, it goes up to positive infinity. So I have positive infinity here. This is infinity over infinity, which is also indeterminate form, which means that we can use L'Hopital's rule to take derivatives of top and the bottom independently, right, from each other, and go from there. So derivative of ln. Actually, you know what? I'm going to let you try this. So try this problem. Try to complete this problem on your own. I'll give you like 2-3 minutes. I'll be right back. Okay, let's take a look. So derivative is 1 over x, and derivative of cosecant is what?
It's cosecant. It's a negative cosecant x cotangent x.
Very good. Very good. All right. So now let's take a look if we can simplify this. So cosecant x is 1 over sine x, and a cotangent x is cosine x over sine x. That will mean that we have to remember how we have to copy this limit all the way to the last step. So that means that we have a situation where we have negative cosine x divided by sine squared x. Now we deal with a double fraction. So all of this is equal to the limit x goes to 0 plus. And when you deal with a double fraction, sine squared goes on top. So we can call that negative sine squared x divided by x cosine x. Now, try 0 again. When you try 0 now, you get 0 over 0. Because sine of 0 is 0, and then you square it, it's still 0. And when you plug in 0 for x in the denominator, that's 0 times cosine. Cosine of 0 is 1, but 0 times 1 is 0. So we still have 0 all across the board. So now, what we do is we do the L'Hopital rule again because we have 0 over 0. But in this case, right, for our, we, again, taking the derivatives and all of that stuff, so we see that we can keep taking, right, derivatives and L'Hopital's rule many times if we need to. So we're going to keep going and doing this as many times as we need to obtain the value. So derivative of sine squared up there is -2 sine x, and then the derivative of sine is, there is a cosine x there, divided by, and derivative on the bottom is the product rule. So copy the first, derivative of the second, plus copy the second, derivative of the first is 1. And now, if you plug in 0, you see that the top goes to 0, this one goes to 0, but this one goes to 1, which actually gives you 0 divided by 1, and the answer is 0 in this case. So that's the deal. So we were able to find the limit, right, using the L'Hopital rule, and this time around we had to use it twice. Now you might also remember those limits when x went to infinity and you had, let's say, x cubed plus 6x minus 9 divided by I don't know, 4x cubed minus 1, for instance. And in this case, right, your job was to divide everywhere by x cubed, and when you divide everywhere by x cubed, you take a look at the values and so on. Well, that's all good, right? We can still use that method. But if you are to plug in infinity, in this case, you will get infinity over infinity, which means that we can also solve this problem using L'Hopital's rule. So, oops, missed that one. There we go. So this is actually infinity over infinity, and we can use L'Hopital's rule to come up with 3x squared plus 6 divided by 12x squared. Now you check it again, and you still have infinity over infinity. Okay, we can use L'Hopital again. We learned that we can do it multiple times, right? As long as you have 0 over 0 or infinity over infinity, just go for it. So this is going to be 6x divided by 24x. Okay, I still have infinity over infinity because I have this 6 times x and 24 times x. So now I can use L'Hopital rule again. So this is what? The third time that I'm using it. And it's 6 over 24. Well, that's 1/4. And now, what do we know? When powers are the same, you can take their front coefficients. Yes, 1 over 4. You learned that in pre-calculus course. Or you learned that when you divide by x cubed, 1 over 4 will survive because everything else will go to 0. That was in chapter 2. And now with L'Hopital's rule, you are getting the same 1/4 answer using, right, derivatives. So that's what L'Hopital's rule is. And it only works, you only take derivatives when you have 0 over 0 or infinity divided by infinity. That's it. That's the end of the story. Now we study the forms that are not 0 over 0, infinity over infinity, but they can be converted into 0 over 0 or infinity over infinity so that we can solve those problems. So, L'Hopital rule only if we have 0 over 0 or infinity over infinity. Now, in this lecture, we're going to study 0 times infinity. We're going to study infinity minus infinity, which is another form of this. And we are going to study 1 to infinity, 0 to 0, and one more. I think it was infinity to, yeah, infinity to 0. Good. So these are the other 5 that we are going to convert into these and then use the limit. So your L'Hopital rule is just the tool that we learned, right? That we've seen so far. Now everything outside of that is going to be what we learn, the methods and so on. So let's go and talk about 0 times infinity case. Now, if you have f of x going to 0 and g of x going to infinity, say, right? And they are of the form f of x over g of x, there is a very easy trick, right? So this one is going to, let's say, 0, and this one is going to infinity. There is a very easy trick to rewrite the function, and the whole problem becomes much easier. See, the algebra rule, maybe orange, I guess, I don't know. F equals 1 over f. So this is a really interesting. Oh, guys, I was like, what the hell is wrong? This is supposed to say f of x times g of x. There we go. So now, there we go. So this one was the one going to 0, and this is the one going to infinity. Now, look what I'm doing. I'm going to change f to 1 over f. Now that means that this will change into g of x divided by 1 over f of x. Now, remember, g of x was going to infinity before, still going to infinity. But now, remember that your f of x was going to 0. If f of x is going to 0, then the whole thing over here is going to infinity, because it's 1 over 0. And we know that 1 over 0 is going to infinity. Take a look at 1 over x graph. I don't care which way you approach it from. As your 1 over x goes to infinity, if you approach from this side, you're getting positive infinity. If you approach from this side, you're getting negative infinity, right? So 1 over 0, 1 over approaching 0, is going to be approaching positive or negative infinity, but it's infinity. That's all we care about. So if it's 1 over approaching 0, which is what we have here, 1 over approaching 0, because f approaches 0, then the entire expression 1 over f approaches infinity. So it's a very easy and clean algebra trick to transform our functions, and this is all we use. So now let's take a look at the problem that would use something like this. So let me see if we can find an example. Now, the problem in the homework is they mushed all of these problems together. So problem 17 to 83, they just dumped everything in. And technically, it's just like, good luck, right? Good luck, solve this. I want to see if I can find a problem that it's another cosecant problem. That's a good idea. No, let's do the tangent one because we already did a cosecant problem. How about problem 54? To illustrate this idea, it's a joke, right? Just one algebra step. Limit x goes to 1 minus for 1 minus x, and then tangent pi x over 2. Right, so this is the limit you want to find. And obviously, without these, without L'Hopital rule, this would be nearly impossible to, solve. I mean, you can always graph, and you look at the graph, and you can do the chart of values if you are, patient to calculate all of that stuff. But now let's use this. 1 minus 1, so that goes to 0. Call that f and call this g. And when I plug in 1, tangent of pi over 2. Well, tangent of pi over 2 is infinity, right? And how do I know? Because I just know trig. That's how I know. The tangent graph goes like this, and pi over 2 is the vertical asymptote. Now I would say, why would vertical asymptote be at pi over 2? Because tangent x is sine over cosine x. And if you draw cosine x, if you draw, so if you draw sine, pi over 2, so sine is 1. Cosine is 0. So you see that at pi over 2, you must get the vertical asymptote because you're dividing by 0 there. So I just know that. And as I approach pi over 2, right, from this line, because again, I plugged in 1 for x and I got cosine of pi, tangent of pi over 2. So as I approach the tangent of pi over 2, I'm getting infinity. Boom. So this is my problem. Now I have two options. One option is to take f and write it as 1 over 1 minus x, or to take a tangent and write it 1 over tangent pi x over 2. So in some problems you go one way, in the other problems you go the other way. It depends on the problem. And the rule of thumb is that, if you're running around and you hit the brick wall, turn around and run the other way, meaning try the other function. So I'm going to flip the first one, but flipping the second one should not be issue, right, at all. We'll see. I don't know. Maybe we have to flip the second one. So L'Hopital, no, sorry, not L'Hopital yet. Aha, this is algebra now. So we are going to leave the tangent of pi x over 2 on top and write this function on the bottom this way. And now we're supposed to differentiate and see, right, what we get. Now look at this. The derivative of the tangent is a secant. Oh, by the way, we check again and we get infinity over infinity, right? So this one goes to infinity because it's again tangent of pi over 2. Tangent of pi over 2 goes to infinity. Good. And now look at the bottom. You have 1 over 0. 1 over 0 also goes to infinity because you're dividing by 0. So now is the time to do L'Hopital's rule because we have infinity over infinity. And this is where the problems start. Let's go to the next line. This is where the problems start because now the question is, are you going to get something in quotation mark nice so that you can work with this? So derivative of tangent is secant squared. So that's a secant squared pi x over 2 with the pi over 2 in front because of the chain rule. So that was our derivative of tangent. And then derivative in denominator, I'm going to use my favorite chain rule. So it's negative 1 minus x to the negative 2, and then times minus 1 from the chain rule from the inside because it's a negative x. So the whole thing is positive 1 over 1 minus x squared. Now, we can clean this up and see what we have. Maybe we are able to solve it, maybe not. If not, we're just going to go back and swap the functions. So we have pi over 2 multiplying everything. I could have kicked that in front of the limit as well. And now I have my division line. Now, secant is 1 over cosine, and over here I have 1 over the parenthesis squared. So I hope you see that this becomes 1 minus x squared on top, and then the 1 over cosine just goes cosine squared pi x over 2. So write these things out if you don't see it at this point. Now, cosine of pi over 2 is 0, and the top is 0. So it seems like we got nowhere, right? This is going to 0. This is going to 0. So we can do L'Hopital again. Now I'm going to kick this pi over 2 in front of the limit, so it's not in my way. I don't need it for anything now. The derivative on top is 2, 1 minus x, and then the derivative of the inside is negative 1. And the derivative of cosine squared is going to be 2 cosine pi x over 2 to the first power times the derivative of the inside, that's a negative 2, and the derivative of the cosine is negative sine, so that's the negative in front, and then pi x over 2. Now, does this work? And the answer is yes, because you are going to now, we can use the identity to combine this into a double angle. So it becomes, and I'll cancel the negatives. And then this top 2 can cancel the 2 on the outside. So now we just have a pi outside. And we are left with 1 minus x divided by, and when you combine ones on the bottom, you get 2 sine pi x. No, not 2, just sine pi x. 2 is the part of the formula. So sine pi x. And now, when you try to plug in 1, sine of pi is 0, and the top is 0. We still have 0 over 0. Well, let's hit this with another L'Hopital. You know you made it in life when someone makes the verb out of your last name, right? So hit this with L'Hopital or L'Hopitalet. Okay, so now the derivative is, again, goes to 1 minus. Derivative on top is just negative 1, and derivative on the bottom is pi cosine pi x. And we are finally done, because now we cannot take limits anymore. Cosine of pi is negative 1, so we have pi negative 1 over pi, and when you plug in 1 for this one, it's just cosine of pi. Now, cosine of pi is negative 1. If you remember, your function looks like this. This is 0, this is 2 pi, midway is pi, and it's negative 1. So negative 1 goes in here for a total of 1. So this entire problem, right, which you can now go back in YouTube and rewind and watch a couple of times, right, ended up being 1 as the answer. Now, you might say, yeah, there was a lot of calculations and a lot of things, right? Is there a way to verify this? Of course there is a way to verify this, right? All we need to do is to graph the function and make sure that at 1, it gives the 1 as a y value. That's all we want. Because the limit's ultimately fancy way to compute y values, right? So, if I am able to go to Desmos over here, which I had ready, there we go, and I type in this function, which is, let me just get the keyboard attached again, because it's going to be easier to type. So I have 1 minus x, so that's our starting there, and then times the tangent of, and the tangent is pi x over 2. Pi x, don't panic, divided by 2. There we go. And you clearly see 1, 1. It's even a maximum.
Professor, the Zoom people are...
The Zoom people are left out. Yes, Zoom people
Yeah.
are always left out. Wow, no one cares about Zoom people. Hold on. There we go. Zoom people, welcome. Zoom people, welcome. Oh, actually, I have a calculation error somewhere. We're supposed to be getting pi over 2 as the answer, not 1. You see that? So the tangent, let me just check, 1 minus x, tangent pi x over 2. Yeah. So the graph over here reveals that at 1, the value should be 0.577 blah blah, which is pi over 2. So now I have to go back to my calculation and figure out where is my pi over 2. New share, go back to this thingy and share. There we go. Where's my pi over 2? It was probably when I took, there it is. So when I took this derivative, I need to kick a pi over 2 out. So there was supposed to be a pi over 2 in front over here as well. Okay. Let's fix this now. So this pi over 2 is in the denominator, so that will cancel completely. I did not label this. Oh, that's why, because I'm hitting the keyboard. Did I? So let's see, what do I have? X, 1 minus x, that's that one, the derivative here. Then 2 goes down, the negative goes up front. Okay, then this one. That's 2 cosine times sine times pi over 2 in front, and then pi over 2 will cancel over there. So now, when that cancels, the negatives cancel. Now I am left with, this pi is gone, the 2 survives in front. 2 survives in front. And then I have everything collapse into this. Okay, so now this is no longer a pi, this is a 2. And the derivative is -1, and then derivative on the bottom is this, so this is now 2. So it's 2 over pi. Now let's check our graph one more time. It needs to be about 0.6. Oh, this is not pi over 2. It's not pi over 2 is 1.577. That's all the way up. This is 0.6, let's say 0.63. So this better work out to be approximately 0.63 or something like that. So 2 divided by pi. Yep, 0.6366. Good. Okay, so it's 2 over pi. Much better. Fixed. And this is why it's important to look at the graph and verify your calculation, because it's so easy. And the only thing that I messed up was I forgot to do the chain rule. I was focusing so much on the chain rule with a square, and I completely forgot about the chain rule for x. So see, it's very easy to make these mistakes if you are not 100% focused when you do this. All right, I made this cosine graph here either. That's gone. So that was case where we had the 0 times infinity case. You figure out which function to switch into denominator, and if you end up with something that it doesn't really work, all you do is you just abandon it and then switch the other function, and you go from there. So it's not not the end of the world. All right. The next order of business is to talk about infinity minus infinity case, which is unfortunately a lot more work. Infinity minus infinity case has you really chasing this algebra around. And the reason is, when you have infinity minus infinity, let's just take the book example, whatever. X squared minus 3x. All right, so this is the problem you want to solve. And when you take a look at infinity minus, you plug in infinity, you do get infinity minus infinity case, right? So now remember, we can only deal with 0 over 0 or infinity over infinity. And I have a subtraction. So how do I go from subtraction into division? Right? What is the sequence of transformation that we have to go one by one to, right, like step by step, one by one of those transformations to figure out this transformation from subtraction into a division. So we start by understanding that in order for us to get to division, we have to have multiplication first, and then we can use the 1 over f trick from the previous case. But when you have the previous case, right, to get the multiplication, over here you have a subtraction. So you need a subtraction to go into multiplication, and then multiplication to go into division, right? So it's a long algebraic procedure. And it's very simple, right? Because over here you have to factor. And then from here to here you use 1 over f. So it's a very structured approach. It's just that, it's a lot of steps and a lot of algebra. So now that we know the path, call this the path you must take on this epic journey, right? You have the subtraction. The job is to factor. Now, obviously, I would need an x here to factor it. Now, that x I can push from the root. So let's go. Limit x goes to infinity, x minus square root of x squared 1 minus 3 over x. So what I did is I factored out an x squared inside, so that when that x squared escapes the root, it becomes x in front. So limit x goes to infinity, x minus x, square root of 1 minus 3 over x. So this is our first part. Now we're going to do the next step, which is factor out x, and we finally are getting our multiplication done. So now when you factor out x, you are left with 1 minus the square root of 1 over 3 over x. So now, what are you getting when you plug in infinity? When you plug in infinity for x, you obviously get infinity. When you plug in infinity for 3 over x, you get 0. And then square root of 1 is 1. So you have your infinity times 0, which means that we can now use 1 over f to do the transformation. Maybe this should be orange. Boom. Come on. There we go. So now, when I use that transformation, I have limit x goes to infinity, 1 minus 3 over x, and then this is 1 over x, because this first function I decided to put down into denominator. So now that I have this in denominator, I'm going to see that I have 0 over 0. We already described how the top is 0 because, right, 3 over infinity is 0, and then you just have a square root of 1, which is 1. So 1 minus 1 is 0 on top. And on the bottom, you have 1 over infinity. That's 0 as well. So this is where we can use L'Hopital's rule to come up with, this with derivatives and see if we can solve it from there. Now, the denominator is easy, right? Negative 1 over x squared. The top is more involved. Derivative of 1 is 0, so that's gone. Everything has to be negative because of the minus sign here. And the derivative of this square root is always 1 over 2 times the same square root times the derivative of the inside. Now, the derivative of the inside of this square root is the derivative of 1 minus 3 over x, which derivative is 3 over x squared. I hope you see that, because the derivative of 1 over x is negative 1 over x squared. That negative kills the negative, and then times 3. So when you take this derivative, you multiply it by 3 over x squared. That was the chain rule. So that's further equal to the 1 over x squared, the negative, and this cancels, and you just get the 3 in front. So you have, oops, I forgot the limit, points off. Limit x goes to infinity, and you are left with 3 over 2 square root 1 minus 3 over x. At which point you can plug in your infinity, because 3 over infinity is going to be 0, so you get 3 halves. Who would say that infinity minus infinity is 3 halves, huh? It depends on a function, obviously. That value changes as soon as you change function a little bit. it changes. Namely, this: if you change in a problem 3 into a 5, it will propagate all the way through, and you would get 5 halves as the answer. So you can literally make it anything, right? You can make your infinity minus infinity to be any value you want. It's not that difficult. And yeah, that's infinity minus infinity. So your job is to factor and do actually a lot of algebra there. It's a lot of algebra steps. And then at the end, you just take the limit, which was very, very simple. But those derivatives with chain rule, like people trip over these derivatives over here a lot. So be very careful with these derivatives, and it's always, always, always good to memorize these derivatives because they show up a lot, and they just make a lot of mess if you have to keep computing them every time. So the derivative of 1 over x is negative 1 over x squared, and the companion, right, the derivative of square root of x is 1 over 2 root x. It's so much, life is so much easier when you don't have to waste time, and stop for those. Like you can post that sign, we break for no one. So now you can go and figure out a lot of these, let's 62. Let's try one of the trig problems, and I'm going to leave you actually some time to try this on your own. This was on the exam or the final at one point, I don't know. Tangent theta minus secant theta. It's a really straightforward one, but I don't know. People find a way to complicate things, so let's see what you get. So what is the thing that we have to factor? Did anyone figure out?
Is it the cosine?
Nice. Well, 1 over cosine.
Yes.
Mm-hmm. So tangent is sine theta over cosine theta, and secant is 1 over cosine theta. So we can factor out one over cosine theta, and we are left with sine theta minus 1 in parentheses. Now, when you plug in your pi over 2, your cosine theta is infinity. I mean 1 over 0, which would be infinity. And sine gives you 0. Because sine of pi over 2 is 1, 1 minus 1 is 0. So that's what we have. So now we're going to do the trick of 1 over a function, and we have the limit. Theta goes to pi over 2. I'm going to switch the cosine, and if I write 1 over 1 over 1 over cosine, right, that just works out to be cosine theta over here with ridiculous amount of these. And now we have 0 over 0 again, which means hit it with the L'Hopital. That's limit. Theta goes to pi over 2. Derivative of sine is cosine theta, and derivative of cosine is negative sine theta. And now when you plug in pi over 2, you get 0 over 1, which is 0. So the limit over here is 0. And again, if you are to go and graph this, right, it better hit the x-axis at pi over 2. Or get close to it. All right, so the only, well, there is another concept after these exponential ones. So the only ones that are left as cases are exponential cases. One to infinity, 0 to 0, and infinity to 0 cases. So these are the ones that we have to explore. Now, these will be using logarithmic. We're using logs to go through this. Now, the most famous example is the limit x goes to infinity of 1 plus 1 over x to the x. This is insanely important because this limit will show up many times in Calc 2, and it will just have n's instead of x's. And if you guys don't know this limit, then you are going to have a lot of trouble, obviously, in Calc 2. So make sure you know this limit very, very well. All right, so what are we going to do now with this limit? Well, as before, we set this equal to y. Well, actually, you know what? I'm going to do this in a separate step. and then we squeeze in ln on both sides. Now, there is a proof why ln and limit can swap. Has to do with ln being increasing function and all of that kind of stuff. But our step here is to swap the ln with the limit, and now you have ln of 1 plus 1 over x squared, raised to the power of x. And then what you do is you go and bring that x in front of ln, and it will show, right, what to do next. So staring at the problem doesn't help. I mean, you always write it down and see what the next step is. You're not playing chess over here on a Grandmaster tournament or something. You just, write the next step and say, okay, so once I'm here, the only thing I can do is to kick this x over there. Then once that is done, now, okay, I can check, because I have multiplication of two functions. Let me check the L'Hopital rule situation, maybe that I can achieve something there. So it is now going to, when you plug in infinity, this one is going to be infinity. And when you plug in infinity, ln of 1 is 0. Aha! I have the situation. So let's go. ln y, and then we are using L'Hopital. So we are going to, oh no, not L'Hopital yet. I have to switch it first. So ln of 1 plus 1 over x divided by 1 over x. So this is where we use f is equal to 1 over f. That's what we have. All right, so now what we are going to do is we are going to take this situation that we have 0 over 0 now, because over here you have 1 divided by infinity, that's 0. When you take one unit and cut it infinitely many, each piece that you're left with is of the size 0. So now that you have this situation, we are going to go and take a look at the derivatives. So, oops, don't need to be dramatic yet. So ln y, and now we do the L'Hopital. Keep the limit there. And now we have to take the derivatives. Now I told you to memorize the derivative for 1 over x, because you're just going to use it so much that the sooner you memorize it, the better. Okay, so what are we going to do? We are going to now take the derivative on top. Now it's ln of something, so we know it's immediately this. Write the function as is on the bottom and put its derivative on top. And its derivative is just that. Now, over 1, you can quickly see that these are on opposite sides of the fraction, so they can be cancelled. And what you get is limit x goes to infinity of 1 over 1 plus 1 over x. So ln y is 1, right? Because when you plug in infinity, 1 over infinity is 0, and then when you add that to 1, just 1 over 1 is 1. And now you solve this, you e both sides. Maybe I should do that orange or something. There we go. So we get y is equal to e to the first power, which is e. Now remember that we set the entire problem equal to y. So if y is equal to e, then this is equal to e. And there is your calculus definition for e. right? The one letter that you memorized, right? The 2.71828 blah blah in your pre-calc course. Now you know what the calculus definition for it is. So the limit when x goes to infinity of 1 plus 1 over x raised to the x is equal to e. I don't want to exaggerate here, so I'm just going to do a few of these things. This is going to show up a lot later on. I think this should do it. Maybe add one more. I don't know. There we go. Now there is
no rainbow.
Sure. This one, right?
That's the one.
We'll just add a little bit. There we go. Perfect.
Now I understand.
Now, a little modification on this. Limit x goes to infinity of 1 plus a over x to the bx like this is going to be e to the ab. So if you change that 1 with a, so let's say put a 3 there, and you still have b to be 1, then it's e cubed. So you can affect this formula very easily, right, with these values. So not such a big deal. All right. So the next problem, and we can literally pick up any problem from the homework, which is where I'm going to jump now. Let's take a look at 76. It's limit x goes to 0 of 1 plus 4x raised to the 3 over x. All right, well, that's 1 to infinity case. I hope you see that. Because when you plug in 0, 4 times 0 is 0. So you have 1 raised to 3 divided by 0, that's infinity. So 1 to infinity. That is one of our forms, so we know what to do. Set this equal to y. Oops, forgot the x. And snuggle in this ln. And then swap ln and limit. So try this one on your own. Try it and then let's see how it works. If you have a question, it's a good time to ask. I'm alive. Don't panic. Let's see. So ln y, swap these guys, and you know that 3x will go in front. And we have this. So now we check. We have 0. So 3 divided by 0 is infinity. And when you plug in 0 for 4x, it makes it ln of 1. ln of 1 is 0. Maybe I should write that just in case, so you are not confused with that. So now we flip. There we go. So 3 over x, when it goes down, it will change into x over 3. Now, just in case, I'm going to write that step on a side. 3 over x is equal to 1 over 3 over x, which is 1 over x over 3. So that's the key part. It makes everything easier. So now you can see it's 0 over 0 easily, because when you plug in your x equals 0, divided by 3 gives you 0 in denominator. We take some derivatives and we are done. So this is actually a very fast problem. So L'Hopital rule, we take derivatives, just 1/3 in denominator, and on top we have 1 plus 4x and 4 on top, which is limit x goes to 0, 12 over 1 plus 4x. And when I plug in 0, I get a 12 there. So ln y is 12. And when I e both sides to get y out, we get that y is e to the 12. So the limit, the problem that we are computing, of 1 plus 4x raised to the 3 over x is equal to e to the 12 as x goes to 0. Again, easy to verify, because all you need to do is to graph this and see if the y value is e to the 12. Now e to the 12, obviously it's large numbers, so good luck scrolling through the graph to figure things out, but it's possible. So we use logarithmic differentiation, not logarithmic differentiation, but that logarithmic approach, just like we used for logarithmic differentiation. We use it here to deal with all of these exponential kinds, right? The cases that are these ones, 1 to infinity, 0 to 0, and infinity to 0. Good. So what is left? The only thing that is left is to talk about the ordering of these functions, meaning growth rates. And I'm going to really emphasize growth rates. This is a very important concept, especially going into Calc 2, because you don't want to take the limits when you don't have to take them. If you are able to through this knowledge, just quickly figure out what the limit is, then there is no reason to compute. Now, growth rate of functions. Let me just give you a quick rundown of what we are talking about here. So I can take basic counting, let's call it x, and just put 1, 2, 3, 4, 5, 6. That's good enough. Now I can make that linear by multiplying, let's say, by 2. 2, 4, 6, 8, 10, 12, right? And we see that this one grows faster. So if x grows this way, then x squared grows that way. It's faster, gaining y values quicker. But then we have x squared, which is 1, 4, 9, 16, 25, and 36. We see that's growing even faster than what we have. Then you say, okay, how about exponential 2 to the x? Now that one is going to be 2, 4, 8, and you're saying like, yeah, it's losing. Well, 16, 32, 64. Whoa. This one would be 49 on a 7. This one is 128. You see how this exponential function kind of in the beginning, it needs kind of time to kick in, but then it just goes, and that's exactly what you see in the graph, right? For exponential function. See that slow part there? That's a slow rise. That's exactly this part here, a slow rise that matches all of the previous ones. And then it just goes, bam, goes up really, really high. Now, we are skipping one of these. It will be plugged in later on in your Calc 2 class. So for us, the one that I call the boss is this one. 1 raised to 1 is 1. 2 squared is 4. Not a big deal, right? They're all pretty much there, right? It's with 3 and 4 when it really goes crazy. It goes 3 cubed. That's 27. Look at the other numbers. It's already gone. 4 to the 4th, that's 16 squared. That's 256 on this line. And then 5 to the 5, I don't even want to compute this by hand. So 3,125. 6 to the 6 is 46,656. Right? Don't even worry about 7 and so on. So what we see here is how quickly these formulas grow, right? As you do this. So we have the ranking rates as x goes to infinity. And the ranking goes like this. ln is slow. Faster than ln is any polynomial. Faster than that is ln times this x to the p. But then faster than all of that is your exponential. Oops, that's not the way we write exponential. There we go. And then we have the boss at the end. Now, why is this so cool? Because I can just, when in some cases, right, I can just look at the problem and just give it a solution and walk away. Limit x goes to infinity. Now that's a requirement. We see that that's a requirement. This doesn't work if x goes to 3. But if x goes to infinity, and you give me x squared plus 6x minus 1 divided by e to the x plus 2, I immediately know this is 0 without talking. Because I am that's that one, exponential, and this one is here, polynomial. So what I have is technically a limit of slow divided by fast, and that limit is 0 because slow one will sluggishly climb up and the denominator will go to infinity much faster, and you're dividing technically a number by infinity, which answer is always a 0. So this is mathematically bad thing to write, but it's so damn easy to remember, right? So slower functions divided by a faster function as they go to infinity, the answer is always 0. If I take, let's say, limit x goes to infinity, and I take the boss, and I divide that by, let's say, e to 1 million x, this is still equal to infinity, because I have the limit of fast divided by slow. Now you'll say, whoa, hold up. You're not going to label exponential function as slow. Oh yeah, I am going to in respect to the boss, right? Yeah, exponential function is really fast rising function in comparison to the polynomials and all of this joke on the left, the square roots, the ln's, right? All of that stuff. But that's nothing in comparison to the boss, right? X over x, because that one, as you can see, grows really quickly. So just compare what's happening for number 6, right? One is at 64, the other one is 46,500, right? So that's a huge difference, right, in growth. So when you have problems now for limits, right, this is an additional tool that you can add to your arsenal, but it only works when x goes to infinity. It doesn't work otherwise. And with this, 4.7 is over. I hope you're not disappointed. You have the indeterminate forms of 0 over 0 and infinity over infinity. Everything else has to be converted into it. So L'Hopital rule only works on those two cases. And then everything else has to be massaged some way or another into those two forms. And then now we have this little, which is actually huge. Guys, your entire calculus 2 is n goes to infinity. I mean, entire chapter 10. No matter which section, gonna find whatever Calc 2 course, it doesn't matter, and pick anything in chapter 2. It doesn't really matter what I pick. Every single limit for the entire chapter, every single problem is the limit of n goes to infinity. So if you don't know limits, and if you can't do L'Hopital's rule, I'm sorry, but there's no Calc 2 for you. It's a very simple. Don't sign up, because you're gonna waste 2 months and somehow get to chapter 10 and then you're just out because you can't take limits, right? Learn this stuff very well. Grades are irrelevant. Calc 2 is coming up, right? And every single problem, as you have seen, I just showed you one out of 10 lessons in there, but trust me, every single one is going to be a limit problem where n goes to infinity. You are going to use L'Hopital's rule a lot in that class. You are going to use the rainbow equation, right? Where you requested the rainbow to be added to it. There you go. This one will pop up many times in chapter 10. Chapter 11 is power series, which is more limits and more, but it's also involving more calculus in it with derivatives and integrals. So yeah, that stuff is coming up, and obviously, right, you need to know the trig, and then you can go into Calc 2. All right, that's it for this lecture. Bye.